All right. So everybody else has a calculator of your own? Cool. Or you don't trust me with your ID? I don't blame you got that kind of face, I guess. Shifty. Okay, so if you want to play along, let's take a look at a few things. So just to kind of get into what the problem's talking about, let me explore a few more things you could do with this calculator. If you have a calculator, go ahead and put this function in. Remind me, where do I go to put a function in so I can graph it? Y equals, it's crazy. So go to y equals and just put that function in. Now you all should know what that would look like. The shape of it. The question is, where the hell is it? All right. And once you get that hit graph, mine looks like this. Does it look the way it should? Not really. But so why might it look weird? What about 8x squared? I mean, 8 is a big-ass number. It's going to rise really quickly. Right? 8 is positive, so it's going up. And the larger the number is, the skinnier it is, the quicker it rises. So this bad boy is rising really fast. So what I'm seeing maybe is just like one arm of it hugging the y-axis. I can't see shit. I can't really see the function itself. Right?
What are you pressing after you put the function in to spit that out?
The graph. You hit to get here. Yeah, hit graph.
I'm getting an error.
What error? What's it say? Dim.
Window range.
Oh, okay, cool. All right. Anybody else? Their graph doesn't look exactly like this, or you got an error? What's it say?
Same window range. Window range.
Window range. Okay. And yours says window range. Okay. So the problem there is like the window could be x min from -5, x max to 5. That makes sense, right? But right now in your window range, maybe it says x min 5, x max -2. And your calculator's like, I can't fundamentally change how numbers exist in the universe, so that's an error. So here's how to take care of any shit like that. When you put a new function in, you almost always want to hit zoom 6. And then everybody should have the exact same picture I do. And the error should go away. Because what zoom 6 does is it makes the window range from -10 to 10, -10 to 10. Cool. So what does that mean then? Where could this function? I could actually see a little bit of it. You might mistake that and not think that, but that's a little bit of it right there. That's that kind of like weird, freaky thing that's stuck to the y-axis. That's part of the graph. But the rest of the graph is somewhere else, because I'm only looking -10 to 10. What if it goes around and then it comes over here up at 70? I'm not going to see that. It's way the hell over there. So here's a couple ways to get a feel for where things are. Here's a beautiful thing. You ready? What did we do when we first learned how to graph? You first make x, y tables. In fact, we made them here because we're learning new functions. We don't know what the hell they look like. Look right above where it says graph. What does it say right above that? Okay, that sounds promising. Why is that promising? Because then I see actual points. I get an idea about where this thing is. So everybody hits second graph to get into table. Well, yours might not start at 0. Let me know if yours is different.
-3.
Okay, cool. You can just hit the down button. You can scroll down. Sweet. Anybody else got freaky stuff in there? Everybody else able to find where I am here? 0, -6, 1, -90. Can you do me a favor? What's happening here? It's going down, down, down. Now, which way do we say this thing should open? Up or down? Up, because the 8's positive. So here it is, it's going down, 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 really fast. Of course it's really fast, because it's 8. The slope is like 8 in a way. Not really, but it is sort of. So it's going down really, really fast. What's the most important point on this parabola? The most important point. On any parabola, what's the most important thing?
Vertex.
Yes, that's where it's going to turn. Can we see that point yet? And you guys are like, how the hell would I know? I don't know what the point that is. But see how it's just still going down, down, down? So keep scrolling down. See if you can identify about where the vertex is.
12, 6 to 42.
So let's see. Well, I mean, let's see here. Blah, blah, blah. Do you see what happened right here? It was going down to 270, and now it's going back up. So the vertex is in here somewhere. It's not a nice number, you can imagine, because you could do negative b over 2a. It's going to be kind of gross, but it's in there. You guys, let me stop here for a second. This is looking at what we know in a different way. We know there should be a place where it turns. We know this thing opens up. So if it's going down, 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 at some point it's got to turn and go up, up, up. And we found about where that is. Now, what's wrong with our window then? Right now, if I want to see at least the vertex, what's wrong with the window? It goes from negative 10 to 10, negative 10 to 10. What's the immediate problem? What am I not seeing? I'm not seeing the vertex. So what do I need to change? It's going from negative 10 to 10 on the x-axis, negative 10 to 10 on the y-axis. If I made the y min, for example, negative 20, I could see further down, for example. Where's the vertex, roughly? Around 270. So how far down do I want to be able to see? Maybe a little bit past that. So let's go to where it says window. Right here, it says window. So what should we change?
The x-axis, the y-axis.
The y min. That's the lowest y I can see. Maybe let's make it what? Let's make it negative 290. Just to be sure we can really see that vertex. Everybody with me? And remember, this is a negative button. Don't use the minus button. They're hardwired differently. You get a little syntax error. Change the y min and then hit graph. Look at that shit. Look at that shit. Now, I want you to figure out what are the next most important points on a parabola. X-intercepts. Can I see both of those? No. Do something right now so you can see both of them. Alright, so what do you guys change? What do you change? X max. Somebody give me a number you made it. 20, 15. Alright, I'll do 18. Just to split the difference. Let's see if that's far enough. Yeah, cool. Alright. So now I want to go a little further with this. Now I can see all of my kind of most important points. Can the calculator find them for me? Because it freaking plotted all these points. It's got to be, it should be able to tell me what the hell the vertex is. It's a point it plotted, so it should be able to tell me. So here's the really cool thing. If you get a graph, all the top row is about graphing stuff. Y equals is where you put it in. Window is how you control what you see. Zoom does the same kind of thing, just in a more, less detailed way. Trace does exactly what it sounds like. You can trace and it can tell you what points it's going through. And then the graph one is obvious. But look above trace. Calc. So I actually want the calculator to calculate something about the graph that I put in. I want it to calculate the vertex. It's going to do it almost the same way that we do it, the negative b over 2a thing. But the calculator can handle things that aren't parabolas. You can handle funky-ass polynomials that aren't really parabolic. You can find their maxes and mins too. I just gave that away. If you go to calc, which thing I'm going to use to find this guy's vertex? Minimum, 11, right? So you go to number 3. It's going to ask you 3 questions. What's easier quest? You know, I'm trying to see if there are any Monty Python fans. It's going to ask for a left bound, a right bound, and that just tells it where to search. And then it's going to ask for a guess. So just make sure that you're to the left of what you want and hit enter. Now it's going to ask for a right bound, so we're going to go to the right of the answer, anywhere to the right of it, hit enter. And then it's going to ask for a guess, so I'm going to try to put my cursor right at the bottom there. Doesn't have to be perfect, to be honest. I can find it pretty well, but I'm going to put my cursor right about there, right where the vertex looks to be. Enter. And I get this. So the vertex is 5.75, roughly, comma, negative 270.5. Pretty close to what we saw on the table. It wasn't perfect, but we got pretty close to the table. All right, so that seems kind of useful. Right? You can actually check your vertex work on any problem where they ask you to find the vertex. You can make the calculator do it for you. That's crazy. Okay, let me think. Oh, let me go ahead and show you also how to find the X-intercepts. So if you go back into calc, second trace to get in calc. So I want to find, the weird thing is, value is kind of nice. Let me just show you what value does. If you select value, you can plug in any x value that's on the screen. So if I put x equal to -5, it'll tell me what the output is. Of course it will. That's the basic thing a calculator does. You put the function in, I think you can do what it does, calculate what the answer is. The more interesting thing is, what's true at the x-intercept? What's the value of the function at the x-intercept?
0.
So I want to do the second thing. I want to find the zeros. I want to find where's the function 0. That's another way of saying what are the x-intercepts. So I do number 2. It's going to ask me for, where is my poor little cursor? It's going to ask me for, it's going to ask me 3 questions again. Let me do the one that we can actually see. If you're trying to go along this with me, just move the cursor over here. So here's where things get a little weird. So if you're going to play along with me for a second, put the cursor really close to the answer. That's close to the x-intercept, right? Yes, sir?
So since it's left bound, wouldn't you want it on the left side?
I will, but left and right get a little weird when you have very steep and very functions that move around a lot. So what I always do is I say put it on the answer, move twice to the left, enter, put it on the answer, push twice to the right, enter, and then put it on top of the answer, enter. It's left bound, right bound, guess. So put it right in the answer and go once, twice to the left, enter. Put it on the answer again once, twice to the right, enter. And then put it back on the answer, enter. Just to be sure you're really going to the left, to the right. Because when it gets steep or when it's going through really a lot or something, it's kind of hard to keep track. That's how you can find the x-intercept. Now notice something. What should be true of the x-intercept? What should be the value of y? At the x-intercept, y should be 0. Do you see how it's having resolution issues, really? -1 times 10 to the -10. That's basically 0.00, the 9 zeros and then a 1. That's at 0. It's trying to tell you 0 here. It's just not perfect with the algorithm. It stops when it's within a certain distance so that it doesn't go insane. You know, I don't know if you guys follow. So this, when you get something like this, it's trying to say 0. It's just that it can't get right on top of it because of the way its algorithm works. Okay. Maybe. So 1 0 is 11.56. You can do the other one to find the other 0 back there. Okay, I like it. Let me see. One last thing I want to show you. One of my favorite things. If I wanted to find this other 0 up here, do you see how it's just too crowded up here? And then it's going to like put words on top of it. I can't really see what's going on. So let me zoom into this right here. So the way I can do that, the best way to do that, is to do zoom box. This is kind of related to on a crime show when they're like, enhance this area here. So you move the little cursor. So if you're trying to do this with me, go to zoom, and then the first one, zoom box. It should have a little cursor on the screen. You guys, if you're playing along with me, you guys are doing okay? Alright. What this is going to do, this is going to be the corner of a box that you can open up, and then it's just going to zoom in on that boxed area. So if I put my cursor right about here and hit enter, now I can move over and up and open up this box. So I'm going to zoom in on this intercept so I can see better what's happening. Is everybody with me there? And just open this little rectangle. When you hit enter, that's one corner of the box. And then you hit over and up to open the box up. So if I hit enter right now, it's going to regraph this, but specifically that little area. So now you can see there. You can see the intercept. The X-intercept. There it is. So now you can do the same thing we did earlier to find the 0. So if there's ever anything happening in a part of your graph, there's too much shit happening there, just put a little box around and zoom in on it so you can kind of see what's going on. There are functions that do a lot of stuff quickly. So you want to zoom in so you can see what it really is doing. Okay, so that was quite a bit there in a row. It was all really useful stuff, especially when you get into pre-calculus. It's kind of good to know what there is, at least, so you know what you can do with these graphs. Okay, so anything else on the graphing calculator while I got this up here? Yeah?
This
Oh, here we go. Oh, cool. This is actually going, finally, now I can do the question. So, ooh, I like it. So you get a question like this, question 81. It said, plot e to the 0.5x. But on the window, -4, 4, 1 by 0, 8, 1. Yeah. So what they mean by that is, let's all try this one together. Go up here, clear this bad boy out. Don't worry about the bracketed stuff yet. Put the function in, e to the, so your e button is right above the ln button, which makes sense because they're inverse pairs. So if you hit second ln, that's your e to the 0.5x. Again, if you have the newer operating system, it probably puts it up as a real exponent, right? Okay. I'm jealous. All right, now, this, in the book, is their way of telling you, this 1 at the end, by the way, is the scale. I'll show you in the window. These first two are the important ones. That's the x min, x max, that's the y min, y max. X by y, right? X axis by y axis. So if I go into window, x min, let me make it -4, x max 4, scale 1. Y min 0, y max 8, scale 1. And the scale is just where they put the how often they put the tick marks. Made it 2, it's going to put it every 2. So now I hit graph, and this is how they want you to see it. Yeehaw! That's a pretty good window. You can see a decent amount of that. And then you can answer whatever questions they ask. Now what's really cool here is, how did I show you, what if I wanted to know what e to the 0.5 times, what you got, Jeff? 2.716. And I want you to do it with the calculator. Who remembers how I can make the calculator tell me the output or some input? Where do I go?
You store the answer?
Say again?
You store the answer?
Stored? No.
You do second and then calc,
Second trace to get to calc
and then
value. And then you can just put in there 2.716. What if x is 2.716? And of course the calculator should be, that's the most basic thing it can do, is just freaking chomp numbers out, right? So you just put that in and it tells you what the output is, 3.88. Kinda nice. Coolness. Real quick, this stuff at the bottom, that's calculus. Yeah. And here, number 5 is if I put two functions, y1 equals and y2 equals. So there are two of them, and I can see where they intersect. That's number 5. Right, so that's really cool. It's like a circle line. I can see where does it intersect. What are the 2 points where they intersect? Okay. I like it. So again, really, there are several problems scattered throughout the book that I've assigned that are from the graphing calculator. You should try those out. When you turn in homework, it's a little bit weird sometimes what I want from you when it's a little bit of an observation, but just do a rough sketch of what you see. It doesn't have to be beautiful, just a rough sketch. Okay. Anything else about the graphing calculator while I have it up here? And just to show you, remember the table? So see up here where it says table set? Right above window? This is where I can control where the table starts. And it can also, who knows what the little triangle means right there? You can throw it right here, Jeff, there. You can see it better there. What's that triangle mean? Anybody know? Any of your teachers ever write slope in this way? Delta y or delta x. This is our symbol for change. So see how it says change in the table is 1, and it starts at 2. So if I made it start at 15, no, Jeff, 15. And I want to go by halves, 0.5s. So now if I go to my table, it starts at 15, 15.5, 16, 16.5. Gotta love that shit. Of course it should be able to do this. This is part of its job, is to put numbers in, throw numbers out. So now I can collect a bunch of them together for you. Okay. I like it. Alright, so enough of the graphic calculator for now. Unless you guys have more questions, I'll leave it up there. Let's see. Any other questions from later in chapter 12? Yeah. Oh no, freaking out. Okay, there it goes. Okay, I got you. I think this has to be in the book also. What if I told you that? What if I told you? What the world do you think you know? Let's say log base C of, let's just do that. Just do B like that. Log base B of 9 is 2.5. Log base B of 8 is 1.79. Just tell you that. There it is. Do you know what B is? No, but you know this, right? And then I ask you calculate log, good Lord, Jeff. Log base B of 9/8. And all you know is log base B of 9 and log base B of 8. So like if I ask you log base B of 7, you'll be a little bit screwed. You can take a decent guess. Yes?
So would you subtract the 2.5 and 1.7?
Because what's the rule here? Yeah. When you're dividing like bases, what do you do with the powers? Subtract. And now you know both of those. So there's whole sections in the homework that do this to you. They'll say, log base A of 7 is known to be 4.8. And you're thinking, sure. Right? But they're setting you up for just using the formula, the property. Sweet. So don't let that one be too freaky. Just rewrite it using the appropriate property and then just see what they told you. You should hopefully know it. Yeah. Now here's a nifty one. Let me see if you guys get this. Given what I've told you, can somebody tell me what log base B of 3 is? Yes, well, almost. How is 3 related to a number that I know something about? 3 squared is 9, so 3 is the square root of 9. Right? 3 is 9 to the 1/2. So if I do this, I haven't changed the question at all, right? So if I answer this question, it's the same as answering this question. But what can I do with this? Take the 1/2 out. And now it's 1/2 of this, 2.5. 1.25. So that might give you something that you're, at first glance, you're like, okay, this I can get, this is shit, what the hell are you talking about? But then you just try to relate it to one of the things you know something about, because you know the powers can just come the hell out of the way. It's that whole idea of making the base related to what you know something about. Yeah, I like it, I like it. Okay, anything else from homework stuff before we get back? I think we'll do a couple out of 12.5 and then get into chapter 13. That's my plan anyway. Okay. Just to remind you guys how 12.5 works. You guys remind me, actually. So based off of, related to something we just said, how would I solve this here? Now, the unfortunate thing is somebody who will divide by 9 and thinks it does more than it does. How many 9s do I have in this thing? How many 9s do I have? 3x plus 2 of them. So if I divide by 9, I'm now going to have 3x plus 1 of them. I haven't really done much of anything. Yeah, so the whole idea with this one, do I have to use logs on this one?
No.
Could you use logs on this one? Shit, yeah. If it works for a not, it's got to work, period. It just has. But this is an easier way to do it because the bases are related. They're the same. 27 is based on 3. And of course, 9 is based on 3. And now what's got to be true, that is what? 12x has to be equal to 6x plus 4. Okay, cool. I like it. Does that make sense? Please let it make sense. If you make the bases the same, you can focus on forcing the exponents to be the same. If you make them the same, then the equation is true. So what we're really trying to do is what x value makes these the same, and therefore this must be the same. So you eventually get, subtract 86 divided by 6, you get 2/3. Freaky stuff. Now, of course, if I can't do that, that sucks, because that's a beautiful way to do it. But if I can't do that, something has my back. So if I have 211 to the 3 minus x equals 49 to the x plus 1. Oh, this should be freaky. And I love you guys. There's less and less math stamina to be found amongst students nowadays, and that's a true thing. You just need a little math stamina. Some of you guys are like, I'll do a couple steps, and that's plenty. My God, what does he expect of me? Everything. So what do I do now? Are they based on 7? You would hope so. That's 7 squared, but no. That's 7 to some power, I'm sure, but nothing beautiful, nothing good. So what do I do?
Bring them down.
I can't do that yet. Right? I mean, 7 squared, is that equal to 2 times 7? So no, I can't just bring the 2 down. I can only bring the power down if it's inside of a log. So the very first thing I have to do is take the log of both sides. Then I can use the property of logarithms. So all right, who's got it? It doesn't matter. So then what can I do with this power? It can come out front of this whole thing. 3 minus x times log of 211 equals x plus 1 times log of 49. And this is a beautiful problem for realizing if you have stamina or not when it comes to math. Because it is a little bit tedious, right? And I know a lot of people think all of math is tedious. This, I will agree with you, is a bit tedious. It's just bookkeeping. Do not put this in the calculator, replace it with some decimal. That's just going to make it worse. You have to trust me. What do I do?
Find my log 49.
Yeah, you totally could. And then you can just look at log 211 over log 49 as one number. Let's try that one. So then I get 3 minus x times log 211 over log 49 equals x plus 1. I'm curious if you can handle... I'm going to try to show you this. I want you... What would I have to do here? I'd have to distribute this thing, get the x stuff together. Are you with me? Let me see if you can handle this. You know, like, just show it to us. What is this? What is it? Is it a cube? Is it a car? I mean, what is it? Is it a variable? Okay, so it's a number. And what is that number? Do you know what that number is? No, I have no freaking clue. So what do we put in place of a number that I don't know? Or any letter you want. Why would I use x? Because it already is here, right? So normally what we do, I'm going to show you this process, and then if you like it, it's beautiful. You can use it everywhere. So replace this with u. Because then it's easier to write. That's the only reason you do it. So at the very end, should your answer have a u in it? No, you replace it with what it is. Now it's easier to deal with. What do I do with the u? Distribute it. So I get 3u minus xu equals x plus 1. Do you imagine I'd have to write this shit next to the 3, write this shit next to the x, when I can just use u, which means this shit, right? It's called u substitution. We use it a lot, because you can imagine this kind of thing happens a lot. So if I put a u there, it's just easier to look at, easier to write, easier to work with. Now what do I want to do? How do you solve for x? Yeah, I would add this over so it stays positive. It's kind of nice, right? So subtract the 1 over, add the xu over, and then what can I do on this side? Take the x out. Beautiful. Whenever you have more than one variable you're solving for, you don't really. You move it all to one side, take that one variable out that was distributed. So now I get 3u minus 1 equals x times u plus 1. So how do you solve for x? Divide by the shit you don't want. I don't want u plus 1. I don't want it. So then you divide by it. Split. But then what's your answer? Your answer better be what? 3 times this shit. I like it, because that's what u is. Minus 1 over log 211 over log 49. Minus 1. I'm sorry, plus 1. Up. So I replace u with this. I replace u with what it really is. I really hope you understand this is not cheating. This is none of that. I don't know what this is. I just have to carry it everywhere. So let me replace it for a second with something that's a little smaller. And then at the end, I'm going to replace that back with what it is. I like it. So anybody play golf or watch golf? I actually don't like golf, but it just came to my mind for some reason. Have you ever noticed when they do it to the green and it's some other dude's turn, you don't want your ball in their way, so what do? You take the ball, like the little marker, right? So the marker is smaller than the ball. It doesn't get in the way. It's just, I'm going to put the ball back there because I think the marker would work to freaking tip it into the thing. You guys understand? It's just taking the place of the ball for a minute. So I'm just taking the place of all this shit with you. Work with it. And then put it back in at the end so I don't have to rewrite that damn thing so many times. It works really well for this, especially. I like it, maybe. There was a, just to talk about u substitution a little bit more for a second, there was a problem earlier, a bonus problem that was something like this. Let me make it simpler just right now. Yeah. Right? Do you know what 2x minus 1 over y is? No. If I replace it with u, do you see how immediately that's so much, your brain goes, I know what to do with that. So it's really good when either the thing is going to be repeated a lot, or it already is repeated a lot. I just replace it with u. And now, how do I factor this? Careful. Yeah, negative 10. 5, so what's my answer going to be? I would put 2x minus 1 over y minus 10. 2x minus 1 over y plus 5. Didn't change any of the work. It just made the form this was in easier to identify. Then I work with it, and then I replace u with what it really is. That idea of u substitution is really useful. Okay, because I get a feeling that once you guys get into this, it's going to fatigue you a bit, trying to keep track of all these logs throughout. And when you're trying to work it, well, you could do this. Okay. Blah, 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 blah. Oh. So let's look at a log equation, and then we'll get into conic sections. Good? Okay. Let's do log base 4. All right, that'll work. Yeah. So make that 11 there if you started copying already. Okay, so what would I do here? How would I solve this? Sort of. How could I rewrite this addition of logs? The log base 4 of... I like it. So I can consolidate those 2 logs into 1. Right? Because I add powers when I was multiplying the things with like bases. That's the property. Now, how did that property help me? What can I do now? 4 to the third power equals this. I like it. So that's the basic idea of what logarithms mean. That's the power that this needs to be this. So 4 to the third power is this. That's how I can rewrite it, because it means the same thing. So x minus 1 times x plus 11 equals, what's 4 cubed? 64. Cool. Now, of course, I just say x minus 1 equals 64, right? Or, all right, what do I have to do? I can't do that shit, right? Don't be doing that shit. What's wrong with this? What do I need to do now? Yeah, I gotta remultiply this out. It's almost like some fool factored this too early before they got this side of a 0. So I gotta remultiply this shit out, suck the 64 in, and then refactor it, right? So I get x squared minus plus 11, so plus 10x minus 11 minus 64 equals 0. Now it's equal to 0. So I get x squared plus 10x minus... This has to factor because I picked a number that would work. Take it. Yeah, 15 and 5. Yep, and the smaller one's negative, so the answer comes out positive. I like it. So you get x equals negative 15, or x equals 5.
It can't be negative, right?
Beautiful. I like it. Just like radicals. Logarithms are not the same as radicals, but they have a lot of the same kind of feel to them and a lot of the same problems. Logarithms can't handle non-positive numbers inside of them. When I put negative 15 in, that's negative. And so is that. Get away. So why didn't math give me that as an answer? Because if that's negative and that's negative, then this number's positive. I lost information about the fact that they were negative. So it looks to math like there's an answer. But we go back to the beginning. Oh, we're sorry, math. There isn't. What about 5? 5 minus 1 is 4. Log base 4 of 4 is 1. 5 plus 11 is 16. Log base 4 of 16 is 2. 1 plus 2 is 3. So not only is the logs okay because it doesn't make them negative, but we also checked the answer to be sure to right together. So 5 is fine. Negative 15 makes the insides negative. Logs can't handle that. So maybe. So just like radical equations, you got to check your answers. Logarithmic equations, you got to check your answers. Make sure they don't make the log freak.
So if you have an equation where both of the answers come out to not work, you know that you did something.
There's no solution. No.
There's no solution.
Yeah. You know, radical equations, you could totally have one that doesn't have any solution. So what this is really saying is, where's the graph of this intersect 3? And it's completely possible that it totally just doesn't. Right? Well, in this case, it isn't. But in general, it could be something set up so it can't. So it is possible I have no solution. I like it. Cool. All right, so that's a review of the last stuff we did in Chapter 12. We're going to get into this stuff. Let's see if I can find it real quick. Let me first tell you why they're called conic sections. This one might work. It's kind of nifty. Oh, thank God it's muted. Okay, that's it.
With Wix.
Conic sections. In this module, you will learn about conic sections.
Oh, this is too much crap.
And the line that remains fixed
Yeah,
is
you don't need to
called
know all this stuff.
the laterals above.
Too much stuff. Here we go. So if you chop the cone,
Depending on the angle made. These curves are
Here we
called
go.
conic sections.
right there. Okay. So if you chop the cone, oh, you can't really see that again. We have a little model that has gone missing. That's too bad. This isn't overly important for you to totally understand, but I want you to see why it's called conic sections. So we have this, you see, it's kind of nifty. We have this cone this way. They come to a point, and then another cone comes off the other side. So this is actually somehow related to space-time, but we're not going to go into that. If I had cone, and you'll see why I've got two of them in a minute. If I chop it straight across, obviously the shape I make, what's that shape going to be? Circle. If I chop it at an angle, what shape will that be? An ellipse. I love it. Right? And a circle is one where all the points are the same distance from the center. An ellipse is interesting. We're going to talk about its definition. But an ellipse actually has two foci. Right? So I don't know if you guys know this, but all the planets orbit the sun. Do they orbit the sun in a circular orbit? No. They orbit it in an elliptical orbit where the sun is one focus. And there's a lot of comets that have kind of elliptical orbits and what else do I want to say? I think it's pretty good. So there's we're going to get a little bit into a measurement of how not circular something is. There's something called eccentricity. So you can talk about how eccentric an orbit is. That means how far away from circular is it. Now here's where things get a little more interesting. There. Oh, shoot. Let's see if they'll rotate it for me. Oh, that was neat. All right. There it is. So obviously if I chop down through the cone like that, what shape do I make? Parabola. So a parabola is actually a conic section. It's a cross section of this cone, conic section. Now here's where the dude at the bottom comes into play. Oh shit. Oh snap. Does anybody know what that shape is? That's not a parabola, right? It's not a parabola. It's not quite a parabola. It's not this. It doesn't have the same. There's two parts to it. This is one graph. This red line is one graph. The same way when you answer a question, you get two separate sets of numbers. It's still one answer to that problem. This is what's called. I don't know if somebody might have said it. Maybe I misheard you. Hyperbola. Hyperbola is the one that's got parts across from each other. It's sort of like if you took an ellipse and just open it the other way. So now its edges are able to go forever. Instead of they kind of run into each other here. If you open it this way, it's like, I can go forever. Right? So you have comets and so forth that have hyperbolic orbits around suns and so forth. Let's see what else they showed here. Curious. Oh, I like you're really deep into it. Ooh, I like it. All right, I'll stop playing that. That's as far as we'll go. We're going to focus on... Oh, yes.
So for the ellipse and the hyperbola, the way you explained it was the ellipse goes this way and the hyperbola goes this way. Does that have any connection to the and or the union?
Sort of. I liked it because I remember it sort of has a connection. It doesn't have like any immediate mathematical manipulation connection, but remember how your answer could have been for an and, it could be 2 to 3. For an or, it could be this way, right? So an ellipse would be like this, and the associated hyperbola would be like this, right? It should connect with you guys. So in a way, they're sort of related. I like it. I like it. So let's start. I'm not going to make you go through parabolas again. They do get a little deeper into parabolas, but I'm going to let 176 do that to you. I want to introduce circles, ellipses, and hyperbolas. So that's what we're going to focus on in Chapter 13. If you got the updated homework sheet, there's only 2 sections we're doing out of 13. So start with a circle. Well, let's do this. Let's start with a really, really, really basic circle. Let's start with one as a center at 0, 0. And let's say the radius is 1. And let's figure out what its equation will be. Now, a circle obviously, is a circle a function? No, because it fails the vertical line test. Is it invertible? No, because it fails the horizontal test. Correlative. But it's still a thing. It's obviously a thing that we use a lot. It's just not a function. How do I get this guy's equation? Well, here's what I do. I say, here's 0, 0. What's the definition of a circle is all the points on the circle have to be the same distance from the center. Distance. Does anybody remember the distance formula? Yep, square root of. That's your x2 minus x1 squared plus. Remember that was just the Pythagorean theorem. The x side is going to be x2 minus x1. That's how long it is. Y side is going to be y2 minus y1. So here's some point on the circle. Now stay with me now. I know I put the point right there just so I can point to it. But I called the point xy. So really, when I deal with this, it could be any point on the circle. Because I called it xy, so it's just generally any point on the circle. But what's got to be true about that point on the circle? It's got to be the same distance away from 0, 0, no matter where I'm looking, right? Whichever point I pick. So that means the distance from xy to 0, 0 has to be the same. And let's call that distance, I don't know, let's call it freaking r probably, because we know the distance is the radius. So I know the distance I want is r. I want that to always be true when I go from one point to the other. So what's the difference in the x's here? From between these 2 points? X minus 0. Right? X minus, what's 1 point? X. What's the other point? 0. So x minus 0 squared plus y minus 0 squared. So then I get, let me square both sides because I don't like this big ass radical sign. Poor little thing. R squared equals x squared plus y squared. There you go. So circles, this guy's equation is x squared plus y squared equals r squared. In fact, for this guy then it would be x squared plus y squared equals, what's the radius? 1. I like it. Okay, now I could have made the center somewhere else, but I wanted to remind you about the idea of translations. I could have started with the center being at HK, but let me now say we've got an equation for circle of radius 1 at 0, 0. What if I want the center to be at 2, 3? What if I want this to be the center? So then it would go like this. Bam, 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 bam. Poor little circle trying to be a circle. What would that equation be then? Well, how do I move it over to? Which letter does the over? Which letters control the left and right? X. So I'm going to want, so for this circle, the equation would be x minus 2 squared. And what do I want? I want to make the y go up 3, so it's going to be, I like it. I don't know if you guys remember, but my x has to be 2 bigger than it used to be. And my y has to be 3 bigger than it used to be. So the center used to be 0, 0. Now it's going to be 2, 3. All right. Is the center a point on the circle? Is the center a point on the circle? No. So you don't think it's going to work when you plug it in. It's not going to work. It's just the center, and all the points that work are the radius away from it. Right? I like it. And you guys are probably like, you took circles and made them so complicated. What the hell's wrong? But now we have a general formula. X minus h squared plus y minus k squared equals r squared. That's the formula for any circle. And earlier this semester, I think I told you, y equals mx plus b, slope and the y-intercept you can see. If you put a circle in this form, the center and the radius pop out at you. So let's try one out. What if it's not in this form? What the shit am I going to have to do? Well, hopefully some of you guys can realize what's going to be involved here. What process? Here's an example of a circle that's not in this form. Let's see.